So now the question becomes, what exactly is entropy? So I dropped this question at the end of our last lecture. Just think about it. We know that entropy is maximized at equilibrium. And what else is also maximized at equilibrium? So let's look at a specific system, which is a simplistic system or process you could think about for an equilibrium process. Now imagine you have two ideal gases. On the left, you have ideal gas D. On the right, you have ideal gas E. Now they have been separated by an impermeable adiabatic wall. So that's our initial state. Upon removing of this wall or this partition, we end up getting our state 1. Now, at the moment when that wall has been removed, you have D molecule stayed on the left and E molecule stayed on, E molecule stayed on the left and D molecule stayed on the right. It's flipped on my end. But nevertheless, you have the molecule stay on one end. So when we're thinking as the gas molecule, let's just pick one of our molecule of interest. Each molecule, or each D molecule, have 50% chance to stay where it is and 50% chance to move right. Right, so when we say stay left, we say it can still move within that left partition, right? But there's also a 50% chance your gas molecule D can move to the right-hand side. So because of that probability, what we end up having is this state 1 is a low probability state. Where the right-hand side, where your molecule is evenly distributed throughout the entire area, is a high probability state. Or the other way to put it is when we're talking about an equilibrium thermodynamic state, we are talking about that equilibrium state of an isolated system is the most probable state. All right, so a system at equilibrium is a system of highest probability. Now, keep in mind, when we're talking about equilibrium, we're only talking about initial state and final state. It doesn't tell you anything about how fast we can reach that equilibrium state. So the rate to reach that equilibrium, that's kinetic, and that's not something we will be talking about in this class. When we're talking about thermodynamic, we're just talking about, hey, your final state 2 is more likely to be your final state comparing to state 1, given infinity of time. So now we know we have two things that are maximized at the equilibrium state. One is our entropy. Now your ds equals to 0, so your entropy maximized at equilibrium. And at the same time, the probability also maximized at your equilibrium state. So taking that together, we can come up with a hypothesis that your entropy is a function of probability. All right, so what we're writing here, assume your entropy, S, is some random function, f of p. So f here is a random function we do not know, and p is the probability of that system's thermodynamic state. All right. So now what we are doing is trying to find out what that function is. What is that relationship between your entropy and the probability? So when we move on to think about that system that composed of two independent non-interacting parts that's separated by that wall, adiabatic and non-permeable. So in here, when we look at it, what we have is your total entropy of that two parts. Let's say these parts are A and B, right? So your SA plus B, or your entropy of the entire system, equals to the entropy of A plus the entropy of B, right? They're separated, but the total entropy is the addition of these two separated parts. Or since we're using our random function here, let's just continue our random function annotation. So your total entropy, you can write that as some kind of function like H as a function of PA plus B. That equals to, well, again, some random function of PA plus some random function of PB. All right, so what we're doing here is, first of all, we know that entropy is an extensive function. So the entropy of the entire system equals to the sum of each part of that system. And then we're just writing that expression that your entropy is some kind of function of probability. So that's what we're all doing here. And then we want to use a little bit of the probability theory. So in probability theory, when we're saying the probability that two independent events both happen is the product of the probability of each event. So in here, when we're saying that, what effectively we're saying is that your PAB or PA and B happening at the same time equals to probability of A times probability of B. All right, so with that in hand, we can rewrite this expression here to H as a function of PA times PB. And that gives you that random function f PA plus random function G PB. Now, what that means is in order to find what that random function is, we need to have something that, for example, you have h x y equals to fx plus gy. So what kind of function that satisfies this relationship? So the function of xy equals to that function of x plus that function of y. I'll skip the derivation since I'm not your calculus teacher, but the natural result for that is a logarithm function. All right, so what that means is you can write S entropy as some constant K times natural log of probability plus A, where A and K are constants. So if we plug in what we did before, right, so you have like fx equals to k log x plus a, gy equals to k log y plus a, and your h as a function of xy equals to k log xy plus some kind of constant. Well, this one should be b. C, and you write that out, it becomes k log x plus k log y plus c, and your c here just equals to a plus b. Just a quick demonstration in why the logarithm function works for this scenario. All right. So the relationship here we're building is what is the nature of entropy. So entropy is deeply related to the probability of a system being in its equilibrium state. And to be more specific, we have S, the absolute entropy, equals to some constant times log probability plus another constant A. So if your statistical mechanics is good enough, you can actually derive the absolute entropy by understanding how much probable your system is from its equilibrium state. All right, so what is the physical meaning of entropy? It is a probability. All right. And let's put a little bit more specific result onto this relationship between entropy and probability by introducing Boltzmann constant. Now, Boltzmann constant, that's one of your universal constant. Some other universal constant include like Planck constant, or your Avogadro number, or the speed of light. Now, Boltzmann constant is a universal constant that's related to definition of terms like temperature. And let's see how it is related to some other constant we've been using, like gas constant. So, again, these are the systems we saw before. Now we're talking about the transformation between your state 1 and state 2. This process is an irreversible mixing of two perfect gas at constant temperature and pressure to reach that equilibrium state. So, how can we calculate this process? What we have is delta S equals to your final entropy minus initial entropy, right? So here, your final entropy is S2 minus S1. Or the other way to put it is because we know your S is a logarithm function of probability, you can rewrite this relationship equals to K ln P2 over P1, where P is the probability. Right, so P is the probability that your system is in state 1 or state 2. So how do we calculate probability in this case? So first of all, when we think about that probability, let's look at P1 first. So in P1, what we are saying is half your gas molecule just happens on the left half, and the other half of your gas molecule E happens to be on the right half, or the other half. Now, the way to think about it is when you put the probability of state 1, assuming your gas molecules move randomly, you have P1 equals to 1/2 number of your molecule D times 1/2 on the power of your number of molecule E. All right, so what these terms mean? The first one just tells you that's the probability that all molecule D in 1/2. And this one is the probability that all molecule E in the other half. Right, so for every one of it, you have like 1/2, but then depending on the number of molecules, well, that's to the power of ND and NE. So these are the number of D and E molecules. So let's assume your ND equals NE, so you have the same number, but we can definitely assume some other way, right? You can have like 1:2 or 2:1. Now with that in hand, assume ND equals to NE, we can further simplify my P1 to 1/2 times 2ND. All right? And then what about the probability of state 2? Now your state 2 is your equilibrium state. So what we say about that equilibrium state is this one is almost 100%. So it's only infinitesimally less than 1. All right, so let's put it this way. So that's our P1. And my P2, we can assume it's almost equal to 1. So with that in hand, when we rewrite this relationship out, your P2 is almost equal to 1, and your P1 is 1 over 2 to the power of 2nd. So if we write the expression for delta S for this process, we have delta S equals to S2 minus S1 equals to K ln P2 over P1. Or here, P1 equals to 1, and P2 equals to 1, and P1 equals to 1 over 2 to the power of 2nd. So we can rewrite that into K ln 2 to the 2nd. We can take that nd out, becomes K 2nd ln 2. All right, we're not even talking about any specific chemical reaction. This one is just simple probability and just using the probability theory to link your entropy and probability. And then let's move a little bit forward and think about what does my delta S give me. Now we have delta S equals to dQEV over T, or ds equals to dQEV over T. And when we're talking about this irreversible mixing of the two perfect gas at constant T and P, this is something we did earlier, last lecture. We have delta S equals to negative nd R ln chi d minus Ne times R ln chi e, where chi is your Mohr ratio. So we did this derivation together in our last lecture when we creating that reversible pathway for this irreversible mixing of ideal gases. So if you don't remember how we get this equation, I highly recommend you go back to our last lecture and check that out. Now, and this delta S that's solved using the ds equals to dqRev over T must equals to what we solved using the probability theory, right? So that's 2 nd times chi ln 2. And if you have this part, your chi d and chi e, so we know we're assuming that nd equals to ne, so your chi d equals to chi e equals to 1/2 in this case. So what we end up getting is, if we're using this top relationship, what we have is this one here. That's a number of Mohr and your gas constant. And if we're using the probability theory, we have this relationship, and they equal to each other. All right, so that bigger capitalized N, that's the number of molecule of D, and we used it in our probability derivation. And here, the number of Mohr and the gas constant are used when we're using the ds equals to dq reversible over T derivation. And taking together what we have, it becomes quite obvious, is that your nd times k. So here, your number of mole of D, that equals the Avogadro number, times your number of mole of D, right? And these will cancel out. So what that tells us is your K constant equals to your gas constant divided by your Avogadro constant. And your K here, that's our Boltzmann constant, which is one of our universal constant. That's 1.38 times 10 to the negative 23 joule per Kelvin. It actually works the other ways. People define the Boltzmann constant first, and then we have the gas constant equals the Boltzmann constant times the Avogadro number. But it's deeply related in the nature of entropy. Yes?
Could you scroll to number 4, and could you explain why it's not negative? Because isn't P1 on the bottom, so shouldn't the exponent?
Well, P1 is 1 over 2 with exponential of 2 and D.
Okay, thank you.
And this one, we already flipped that 1 over 2 to 2, right? Because P1 is on the bottom. Okay. So this part is more like abstract and conceptual, but I really, really do want to spend this half an hour, although we're behind schedule, to go over the physical meaning of entropy with you. So again, entropy is deeply related to the probability of your thermodynamic state. At equilibrium, both your entropy and the probability maximized at that equilibrium state. Okay, any questions before we move on? Nope, we're all good? Okay, and this part, because it's more like conceptual, you could expect we ask more questions like true and false or like multiple choices on these kind of topics, so just so you know. And we might also give you a hypothetical scenario where you can imagine what's the probability of like state 1 and state 2, and you can calculate entropy that way. Okay, then let's move on to our lecture 9. And we're finally talking about chemical reactions. I had this question a lot. It's like, how come this is a chemistry class? It's not chemistry at all. So we're finally ready to talk about chemical reactions and free energies. Or specifically, when we're saying chemical reactions, we're talking about material equilibrium. Okay? We're replacing reaction to a more thermodynamic type of nomenclature. So before we jump in to talk about chemical reactions, let's refresh our memory a little bit on material equilibrium and also how your entropy relates to equilibrium for an irreversible process. And then we're ready to define our Gibbs and Helmholtz energy, free energies for reactions. And then we'll talk about thermodynamic relations. This lecture note is especially long. It has 21 pages. I actually think I need like 2 lectures at least to go over this lecture. So let's get started. First thing first, material equilibrium. So we went over thermodynamic equilibrium, right? So there are several different types of equilibrium that must be met in a thermodynamic equilibrium. The first one being mechanical equilibrium. That means your system cannot undergo any acceleration. Or thermal equilibrium. So basically, the real definition is a system at thermal equilibrium is you add a non-adiabatic wall will cause no change in your system. And material equilibrium actually contains 2 different types. The first one being no net chemical reactions. So there's no chemical reactions taking place in your system. And the second one being no transfer of matter. So your system is not exchanging matter with its surrounding. So that's the 2 criteria for material equilibrium. And within that like chemical reaction criteria for material equilibrium, you also have reaction equilibrium and phase equilibrium. So for reaction equilibrium, what we're saying is these are the things you already know, but we're just giving it a more accurate definition. For reaction equilibrium, what we're saying is equilibrium with respect to conversion of one set of chemical species to another. So a typical type of reaction, well, you can write any reaction you like gas, hydrogen, and gas, oxygen gives your water. Right. Or we could also have phase equilibrium. So that tells you we're talking about equilibrium with respect to transport matter between phases of the system without conversion of one species to another. So let's assume you have a cup of ice water and also have water vapor around. Now in this process, you have like Q or delta H fusion. We're talking about constant pressure process. And Q freezing. And also like Q vaporization. And Q condensation. So that's just a quick refreshment of your memory. And then let's link entropy to equilibrium once again for this irreversible material changes, for chemical reactions or phase changes. So again, when we're talking about equilibrium, right, so this is the figure that we have seen several times, right, so that's entropy with respect to time. And at the maximum, you have ds equals to 0, so that's your equilibrium. And before that, you have ds larger than 0. Or again, the different way to say it, thermodynamic equilibrium in an isolated system is reached when your system's entropy is maximized. Or if we put it into into equation, what we have is S system plus S surrounding is maximized. Okay. Now let's set up a scenario in your head, a mental scenario. What we have is, first of all, your system and surrounding are isolated from the rest of the universe that's covered by like rigid, adiabatic, impermeable wall. So that's your system, that's your surrounding. Your system and surrounding are in thermal and mechanical equilibrium with each other. Basically means their heat exchange and also mechanical equilibrium has been reached. Then, within the system, we have irreversible chemical reactions or phase changes within that system. And here it says the system and surrounding are being separated by impermeable wall. Basically means heat can go in and out between your system and surrounding, but no material exchange. Because of this impermeable wall, what we have is within the system, you have thermal equilibrium, mechanical equilibrium, but you do not have material equilibrium. Now, with the impermeable wall, for the surrounding, you have thermal, mechanical, and material equilibrium. So your surrounding is at thermodynamic equilibrium, but your system is not. Okay, with me so far? So then we're looking at the entropy of the system where you have irreversible processes taking place. So let's do it step by step. When we're talking about the system and surrounding are isolated from the universe, what effectively we're saying is your dq system must equals to negative dq surrounding. All right, it's isolated from the rest of the universe, and your heat transfer, well, it's an in and out process. So these two are equal but different sign. And using our second law of thermodynamics, your change of entropy will be a positive number as long as there is irreversible process taking place. So what that tells us is your DS system plus the change of entropy in your surrounding must be larger than zero because you have irreversible reactions or phase changes taking place in the system. Okay? Then for the surrounding, we know it is at thermodynamic equilibrium. Or the other way to put it is for the surrounding, you only have reversible processes taking place. So for the surrounding, we have ds surrounding equals to dq surrounding reversible over t. Okay? And then moving on to look at our system. Because we have irreversible processes taking place in the system, we cannot use this relationship. Now your change of entropy or ds system no longer equals to dq system over t because you have irreversible processes. So this one is irreversible. So what that means is your ds system must be larger than your dq system over t for this closed system, irreversible reaction, and thermal and mechanical equilibrium. Okay, so this one we know because your ds surrounding equals to dq surrounding over t. And we know your total entropy change must be a positive number. And after the equilibrium has been reached within your system, then you have your ds equals to dq reversible over t again. Or taking together, what we have is the change of entropy is always larger than or equal to dq over t, where that equal is reached when your system reached a equilibrium. Okay, and one last step before we define our free energy is now we know ds is always larger than or equal to dq, and your temperature is a positive number. Your thermodynamic temperature is always a positive number. So you have T ds larger than dq. And for this closed system, we have du equals to dq plus dw. So your du is always equal to or smaller than TDS plus dW. Okay? So what we're doing here is just using the definition of entropy and also the first law and second law of thermodynamics to get this relationship that your du is always smaller than or equal to TDS plus dW. Now that equal is at equilibrium, your du is smaller than TDS plus dW. Now the problem here is although we have a relationship between your internal energy and your change of entropy, it's really hard for us to imagine a scenario that you keep the entropy constant. It's just like something we human beings are not very capable of doing. So then we can move on and define new free energies that are useful to describe chemical reactions. So before we move on, do we have any questions? Nope. Okay. Now we want to define two new types of free energy. One is called Gibbs free energy. So that is used to describe material equilibrium at constant temperature and pressure. The other is a Helmholtz free energy. So that is used to describe material equilibrium at constant temperature and volume. So let's start by looking at the Helmholtz energy first. So a few things we'll be using. Let me just put them on the board. A few things we will be using include our EU is smaller than or equal to TdS plus dW. And that's something we just derived together. And in here, let's do it step by step. First of all, we have the expression using calculus. You have dxy equals to x dy plus y dx. You should be pretty familiar with that calculus relationship. So that tells us that dTs equals to TdS plus SDT. Or in here, we have this TdS term. So we can rewrite that TdS equals to dTs minus SDT. So that's just using calculus. Next up, we're claiming this process, or let's define a process only considering the PV work. And for reversible PV work only, we have dW reversible equals to negative PdV. So this dW term becomes negative PdV. And taking that all together, what do we have? So we have du smaller than or equal to dTs minus SDT minus PdV. Right, we can move this term here to the left-hand side. We have du minus dTs smaller than or equal to negative SDT minus PdV. Okay? And again, here for calculus, you can rewrite this term to be something like U minus TS, and that smaller than or equal to negative SDT minus PdV. So remember, for the Helmholtz energy, we're talking about a constant temperature and volume process. So at constant temperature, so this term becomes 0. So what we have is the U minus TS smaller than or equal to 0, where that equal is reached at equilibrium, material equilibrium. For this U minus TZ, that's our definition of our Helmholtz free energy. Yes?
How are we able to combine the derivatives for u and ts?
That one is that one just calculus. So this one is just like dx plus y equals dx plus dy. All right. And now given the definition of your new Holm's free energy state function, well, I already tell you the answer. Whether it is a state function or a line integral, whether it is extensive or intensive, it's telling you within that definition, right? So we have A should have the same unit as your internal energy, U. Also, because your internal energy is an extensive state function, your Holm's free energy A is also an extensive state function. All right. Any questions before we move on? Yes.
Can you explain again how you went from that conclusion to that conclusion?
These two are different things. We came here, we did all these derivations, to came to a point that we think u minus ts is of some importance because we know u minus ts equals to 0 for a material equilibrium process at constant temperature and volume. So we manually define a new state function, A equals to u minus ts. And this conclusion here is getting, because your A and U, you can take basically plus and minus of these two terms, right? So they must be the same in nature. So that's why we call A free energy. It's still a form of energy, like your internal energy. Now we know about our internal energy, U, being an extensive state function. So your A, because they're the same in nature, must also be an extensive state function. Okay? Sounds good. Any other questions? Okay. And on top of the Holm's state function, let's work out another free energy, which is the Gibbs free energy. So our Holm's free energy is used at constant volume. Now our Gibbs free energy will be used at constant pressure. And let's do the derivation together. So first of all, we're still using this relationship. Your du is smaller than or equals to TdS plus dW. And now let's use our U equals to H minus PV. So that's the same as like H equals to U plus PV. That's the definition of your enthalpy, right? So using that relationship, what we have on the left-hand side is dH minus dPV is smaller than or equal to TdS plus dW. And likewise, what we're doing is writing that dPV out, and that becomes dH minus PdV minus VdP, which is smaller than or equals to TdS minus PdV. And doing the same thing, this TdS here equals to dTs equals to TdS plus SDT, right? So your TdS can be rewrite as dTs minus SDT. And in here, some of the terms can be easily canceled out, right? So the negative PDV will cancel out with each other. And what we end up having after the simplification is dH minus VdP is smaller than or equals to dTs minus SDT. All right. And then let's move the terms. Let's move this dTs with dt, this VdP to the right-hand side. We have dH minus dTs smaller than or equal to negative SDT plus VDP. Likewise, we can write our H minus TS smaller than or equal to SDT plus VDP. All right, and at equilibrium and also constant T and pressure, we have our dt and dp equals to 0. So we end up having the H minus TS always smaller than or equal to 0. At constant temperature, pressure, closed system, thermal and mechanical equilibrium, PV work only. It's a long description, but if you think about it, normally at a chemical reaction at room temperature and also under atmosphere, it's pretty easy to achieve. And obviously, like what we did with the Helmholtz free energy at constant temperature and volume, here we're defining our Gibbs free energy. G, which is by definition equals to H minus TS. All right, and using the same logic we did before, your Gibbs free energy has the same kind of property as an enthalpy. So your Gibbs free energy is also an extensive state function. Or the other way to think about it is, what about TS, right? T, type temperature times entropy. That is also an extensive state function because you can do like plus and minus of these terms. All right. So we spent some time today, go over the physical meaning of entropy, link it to probability. And then we went over a detailed process of like how to describe entropy for a system undergo some kind of chemical reaction. And what does the equilibrium or material equilibrium mean in that process? And then we introduced two new state functions because they're very useful. So your Helmholtz free energy A equals to 0 when a system only doing PV work, right? So your A, state function A, the Helmholtz free energy equals to 0 at material equilibrium when we're considering constant temperature and volume processes. And your Gibbs free energy, G, which is defined as H minus TS, so that equals to 0 for a constant pressure temperature process. All right, and the reason we're defining these new state functions is because they can be very useful. Like it's easy for us to set up something at constant volume or at constant pressure, but it's not easy for us to set something at constant entropy. But by making this link, we find out, okay, so if your delta A equals to 0, then your system is at equilibrium if we're considering a constant volume process. And likewise, if your delta G equals to 0, then for that constant pressure process, you're at equilibrium, material equilibrium. We'll see applications of these newly defined state functions in our next lecture. We'll also spend some time talking about the physical meaning of these new state functions. And in our next lecture, we'll see how to use calculus to find out the actual relationship between all these state functions we went over, like Gibbs free energy, Helmholtz free energy, enthalpy, entropy, internal energy. So we'll have a set of equations linking them together. All right. And don't forget about the survey. There are like 3 points. And also like try 5-1 again to get those 10 points back.